So, welcome back. We will continue the discussion on Sobolev spaces, especially some density properties and extension of functions. So, let me just quickly recall what we were doing in the previous class. So, we are trying to prove for the spatial domain of a rectangular parallelepiped that this pi a that Cm the set of all m time differentiable functions on pi a closure is dense in Hm pi, and for that purpose we are trying to find a function defined in slightly larger domain, namely this pi a sigma a for sigma bigger than 1, and we define this f sigma x is equal to f of x by sigma. Okay. So, our idea is to prove that this for choosing sigma appropriate, that this f sigma is close to f in the Hm norm. So, that is what. So, it's since there is sigma in the definition of f sigma. So, when you take derivatives, so the sigma powers of sigma appear. So, it is not a difficult computation, but one has to do some careful computation in order to arrive at this approximation. So, this f sigma naught is close to f in Hm pi a norm. Okay. Since f sigma naught, so there is, we can find this 1 sigma naught bigger than 1, and since f sigma naught is defined on a slightly larger domain. So, we can again use its modifiers. Small modifiers are C infinity functions, and they are close to f sigma. So, this for epsilon small. Okay. So, this we have already seen, and so f sigma naught epsilon minus f sigma naught again in Hm pi a can be made small as we please by choosing epsilon small. So, this is the technique we often employ even later. So, okay. So, this, so we want to find a function defined on a slightly larger domain, and then we can take the modifiers to get smooth approximation of functions in a Sobolev space. Okay. And of course, this is for a spatial domain, namely this rectangular parallelepiped, where the extension to a larger domain was easy. Okay. And now we make use of this thing to get an extension result. So, our next again for a spatial domain. Okay. So, just extension result. Okay. So, let me just give a general definition. So, given f from omega to r, any function, okay, give so we want to extend it to a larger domain. Okay, that's okay. a function f from omega tilde to r. Okay, so, this omega tilde is larger than omega is called an extension of f if this big f x is equal to f x for all x in omega. Okay. Of course, this is too general a definition, but when f has certain properties, for example, f belongs to a Sobolev space. So, obviously, we would like to have this big F also to have some similar properties, and more importantly you want to control the norm of big F in terms of small f, and that will see in the following theorem. So, again this is a special case. Okay. So, just so first let me just introduce some notations. Okay. So, let K A be the cube. So, this is cube in R n. So, its length is 2a. So, okay. So, this K A is set of all x in R n. So, special case of parallelepiped. So, this mod x I is less than a. Okay, so, let me use different variables, because later on we just see that. Okay, let me use y instead of x. So, y in R n. Okay, so, this is n. Okay, so, that is the cube. So, the upper half cube is this one. So, let K A plus. So, this is y in K A. So, for simplicity let us take this. So, any coordinate will do. So, I am just for ease of writing taking y n, and we write y as y prime y n. Okay. So, and this one is in R n minus 1. Okay. So, standard notations. So, now we will see that given a function in K A plus, that is the upper half cube, we want to extend that to lower half. Okay. So, let me state that as a theorem, and then I will present a proof, sketch of the proof. Okay. So, let me just state. So, two parts again. Okay. If f belongs to C M K A plus closure, then there exists f in C M. Now, just say K A. So, we are extending it to the so which is an extension of f. Okay. So, in the process we will also make some estimates. So, that is so in the same class. Okay. So, this if it is the given f is in the class CM. So, the extension is also in the same class. Okay. And second one, if f is in HM. So, this is Sobolev space Ka plus then there is an extension f of f such that. So, again that belongs to the same class on a larger domain HM Ka, and so this is more important for us in the analysis of PDE. So, this norm is still controlled. So, this constant times of course, the constant C does not depend on f. Okay. So, that is more important for us. Okay. So, the first one, the smooth class. So, let me just prove. So, there are many computations. So, you should do that. So, let me just draw this. So, this is x n equal to 0. Okay. So, let me just choose a different color. So, this sorry for that. Okay. So, this is x n equal to 0, and then let me so this is Ka plus and this one Ka, the whole thing is Ka, or you can also call this as Ka minus, where yn is okay. This is not xn, this is yn. Okay. So, this one say yn is less than 0. So, if you just want continuity, then reflection will do. Okay. But here we want the function also to be CM. Okay. So, that requires little more work. So, let f of y is equal to f of. So, we are using this notation y prime yn, and it is sufficient to define this for yn negative. So, here is the definition. I is equal to 1 to m plus 1 a I f of y prime and minus yn divided by this I, index I. Okay, so this is yn negative. Okay, and of course fy is just same as little fy if yn is greater than or equal to 0. Okay, so in this way we are at least making an extension of the given function little f to this Ka. Okay, so for yn non-negative it is same as fy, and for yn negative we are making this definition. So these ai's they are constants, where ai's, so there are m plus 1 constants, i's are constants given by, okay, so just I will write down that. So this summation minus 1 by I to the power s ai. So this is I is equal to 1 to m plus 1 is equal to 1. So this is for s equal to 0, 1. So these are system of m plus 1 equation, linear equations, and m plus 1 unknowns, namely a1, a2, am plus 1. And this is just van der Waals system. So the coefficient matrix has non-zero determinant. So we have unique solution for a1, a2, am plus 1. So where do this come from? Okay. So the idea is just in order to get these relations, what you have to do is we have to equate the values of f and its derivatives up to order m, okay, from both the sides. Okay. You take limit as yn tends to 0, and then these coefficients will precisely satisfy this equation. So this is required for the continuity of this extension, continuity, and also continuity up to order m. Okay. So this, that's why this, if just want continuity, then reflection will do. Okay. So this is little algebra you can do. It's a lengthy computation, but you can do that. Okay. So and that gives us, so verify, okay, just I'll verify that f indeed belongs to the class Cm over closure of this. Okay. But our interest is little more. We also want the integrability of these extensions. Okay. For that, so again you just remember this expression for capital F. Okay. So just remember that. Okay. So next, so before coming to the proof of the second one, okay, so you compute this d alpha, alpha is any multi index, okay, so fy square, and then you integrate that Ka minus. So we are interested only in the lower part, because in the upper part it's the given function. Okay. And again you just look at the expression, Okay, so y n so this just y prime here. Okay, so there is no change at all. Only with respect to differentiation with respect to y n variable will produce something. Okay, so just otherwise it is just so this I will write. Okay, first let me write this expression itself. So before integration, just that's better. Okay. So this is less than or equal to, just see that, okay, a I square. Okay. So 1 by I the index here. Okay, just let me write that. Okay, 2 alpha n. So this is the nth component of the multi index, and then d alpha f y prime y minus y n by I square. Okay. Now you integrate over. Okay. So that implies. So this is straightforward from the just you take take the absolute value and square it and use Cauchy-Schwarz. Okay. So if I integrate now over k a minus, so d alpha f y square. So these are all constants. Okay. So just you, so I will put just some constant. Okay. There will be several constants. So just so again I put I, because there is I there, so let me just put that. So integral k a minus d alpha little f y prime minus y n by I square. And now you make the change of variable. So you call this something different. So this is just, I will put again C0 that I comes. Okay. So this integral, okay, too many things. Just verify these things. So this not hard, but okay, I. So this now it becomes k a plus intersection y n is less than a by I. Okay. So d alpha f of, now I put just y square, but that is again, so you just say that this is C0 k and you sum over alpha, and that implies. So this is the one we have, this f of k h m k a minus, okay, less than or equal to little f h m k a plus. But on k a plus, f is nothing but f. So different constants. So we just conclude that k a is less than or equal to some constant h m k a plus. Okay. Remember, still we are in the smooth region. So we are assuming that little f is in Cm, and yet since omega is bounded, all these quantities are finite. Okay, so let us call it 1. And now we will go to the second part. So, second part. So, let now f belongs to Hm Ka plus. Okay. And Ka plus is a parallelepiped. Okay. So, we can apply the previous density result. Okay. So, again let me just show you that. Okay. So, that implies Cm Ka plus bar is dense in so you see that usefulness of the density result. Okay. So, therefore, we can choose, hence there exists a sequence. So, let me use index okay, FL in Cm Ka plus bar such that FL converges to F in Hm Ka. Okay. And now since each FL is in smooth function Cm Ka plus bar, from the first part, okay, from the first part each FL has an extension big FL in Cm K bar. Okay. And each FL also satisfies this inequality. That is very important. So, this 1. Okay. So, from 1 we see that this FL, the sequence FL is a Cauchy sequence. Cauchy sequence in Hm Ka. Okay. And hence converges to some F in Hm Ka. Okay. So, verify. Okay. So, this now simple thing. So, verify. So, now at least we have found a member in Hm Ka. Okay. So, verify F is an extension of F, okay, and F does not depend, this is important. So, all the time we do that, does not depend on a particular sequence, depend on F. So, if there is another sequence converging to F, and then corresponding sequence converging to some other function. So, with some simple analysis you show that the limit is the same. Okay. And moreover, again go back to, so f also has an expression in terms of f. So, just look at this expression. Okay. And we can now pass to the limit in 1 using any sequence. So, let me also write that, and further f satisfies 1. So, that is important for us. Satisfies 1. Okay. The other bound is trivial, namely that so we usually do not state that this side. So, since f is an extension, so we always have this side norm of f h m. This is true for any extension. So, in particular this one is less than or equal to, because f and f they coincide on k a plus. Okay. So, that is trivial inequality. Okay. Further, so taking the again limit. Okay. So, if you just see this relation, okay, so taking limit, so this, let me call it star and make that comment that f has that expression. Satisfies 1 and has representation star. Of course, almost everywhere. Okay, so that is so f also has that similar expression. Okay. So, these results we are going to use for a general domain now. Okay. So, that is next our next goal. So, fine. So, that is okay. So, with these two things I will just go to the next one perhaps in the next class. Okay. Thank you.